Okay, ladies and gentlemen, welcome in. It's Friday afternoon, March the 8th. I'm doing an example problem here. It's the last example from the notes on transverse shear. It's with kind of these bolts that are holding two pieces of wood together. I said at the end of class today that I'd go through this example problem and post it to YouTube. So let's get right into it. I'm going to share my screen and we'll get to it. So here's the idea. We've got these two boards fastened together, as you can see. The shear load that I'm applying here, the transverse shear load, V, is 50 kilonewtons, and we want to determine the required bolt spacing S if each bolt has a shear capability, what a great word, of 15 kilonewtons. I was being a little sarcastic with that word. Shear capability, love to see that. Here we have a 15 kilonewtons, and I think it's just helpful to know that we're talking about a load here. So 15 kilonewtons would be a load. So when it says shear capability, it means like how much load it can take in shear before it fails. Okay. Don't love that verbiage. You would like to see something like shear load, maximum shear load. That would probably be better. That's probably better verbiage. So, okay, let's get into this. What's the idea here? Okay, so these two boards are fastened together. You can sort of see along this particular line here. We've got these fastened together. If the boards were solid, right? Like where they weren't nailed together, but they were fully thick, then they could hold shear at that interface, right? However much the wood can hold, that's how much it would hold. But these things are actually nailed together. And so the only thing that's stopping the boards from sliding together between the interface of the two boards are these bolts. And so what we need to think about is how much shear stress is there between those two layers of that piece? And that's how much shear these bolts need to stop. Okay? So what is the shear stress between layers if the wood was fully dense? Okay? That's how much the bolts need to stop, right? So bolts must hold this. Right? So hold this, THIS. All right. So let's calculate what the shear stress would be if the board was fully solid. So shear stress if board fully solid. Let's put a coordinate system here. My coordinate system is going to be right in the middle of the board. We'll use our typical coordinate system here. X coming out, Y will be up, and Z to the left. There we go, with our nice little right-handed coordinate system. So let's get on with it. Here I'm looking for transverse shear. Transverse shear in this cross-section, if it was fully dense, this is going to be like Vy QZ over IZT. Bang. And if I'm interested in the shear stress at the midplane of this thing, then I'm interested in any point that lies along that midplane. And so my cross-section here, I can pick any point of interest that I want. They're separated on this boundary, but okay, let's just pick some point of interest here, P. What's the shear stress at this particular location? That's what I'm looking for. Okay, so we're given some dimensions of this thing. We can use that to our advantage. Let's get through it. Here, Vy. This is the transverse shear in the cross-section. We're actually given this in the problem. We're told that this Vy is 50 kilonewtons, right? So here, the shear load in this cross-section filled with 50 kilonewtons. We can just put that in straight away. 50 kilonewtons. Next, QZ. Remember, QZ is A prime, Y bar prime. In order to calculate QZ, what we're going to do is we're going to make a line across our piece at the point of interest right here. This is the line defines the variable little t, the thickness. That's the same as this variable here, this little t. And once we've sectioned our cross section, we denote the area above that cut as here R A prime. Right. That little area itself has a centroid. So here it is. And the distance to that is our y bar prime. So we can define these things. You can use the geometry for the problem. And we're going to get here that A prime is going to be this 300 millimeters. So I'm going to work in meters, 0.3 meters, times the half height of this thing, which is 0.1 meters, times y bar prime, which is going to be half of the 150 millimeters. Okay, so that's the first area moment, QZ. Okay, now we have our area moment of inertia, IZ, for the whole cross section, 112 BH cubed. So 112. My base here is 0.3 millimeters. Sorry, 0.3 meters. My height is the total height of the beam, so it's 100 plus 100 millimeters is 200 millimeters, or 0.2 meters cubed. There we go. And finally, my variable t, that is the thickness of the piece. We've already sort of looked at that here. And that's going to be 0.3 meters. All right. So altogether, the shear stress that would exist if this was dense in the middle there would be a value of 125 kPa. Now, that shear is real. All right. It's in that cross section. It's acting on the x face in the y direction. Right. So that is like this shear, right? It's real. It's acting here. Whether or not that wood is dense or not, it's acting. Okay. That tau xy has a counterpart, which is tau yx, which is equal to that value. So also, since we know this to be true, that tau yx is also 125 kPa. Now think about what this is. Tau yx. It's the shear stress acting on the y face in the x direction. Okay. So back to my picture over here. Tau xy, that's easy to understand. So shear stress on the x face in the y direction. And so that's this here. On the x face in the y direction. Okay, no problem. Fine. But what is tau yx? Tau yx is the shear stress that acts between the two boards. It's the amount of stuff trying to slide these two boards apart. So if you were to think about this, if you just look at bottom board, you would see kind of a bottom board by itself. That tau yx is this shear stress here. And this would be in existence sort of between those two boards, okay? It's this shear stress that you need to hold with the bolts, okay? Now, those bolts are at some spacing S, okay? So this is what we must stop from moving these two things together. And so bolts must hold this at midplane. Okay, great. So how are we going to do this? Well, let's look at this board from the top. By the way, if you wanted your coordinate system here, here's your coordinate system. X, Y, Z, right? So we can see that this is on the Y face in the X direction. Okay, tau YX. All right, so let's take a look at this guy and let's look at the bolt spacing from above. Okay. So if we look at this thing from above, what I mean by that is, all right, we're looking down the y-axis, right? And we've got this bolt spacing here. It looks like this. All right, that's our, that's typically our spacing, right? Is this distance here, which we call the spacing S. I also have this dimension, which I know is the dimension 300 millimeters or 0.3. And it's kind of the setup that we have going on. We put our coordinate system on here again. This is x to the right and z down. Now, those bolts need to hold that shear stress between those two boards. All right. And it's going to do that by protecting a certain area associated with each of the two bolts. Now, what do I mean by that? Well, each of these pairs of bolts is kind of responsible for a particular area of the cross section. What I mean by that is, like, these two bolts here need to protect the shear stress in, like, let's say this area here. Okay, so the two bolts here must protect against, like, the tau yx here. Okay, and so this area here is 0.3 times whatever spacing we pick, S, right? The spacing is up to us. It's what we're deciding. And if we make the spacing longer, the bolts need to cover more area for this thing to shear stress to act. Okay. If we make the spacing less, then the shear stress that's acting between the boards is held by more bolts, right? Because we have a smaller like length between them. Okay. So each bolt, we're told, can hold a shear load of 15 kilonewtons. So if we have two bolts for every little area that we're looking at, then the total load carrying capability across those spaces is 30 kilonewtons. Total load carrying capability of bolts along, or I guess in each of these areas that we've specified. Sorry about that. I think the headphones went off. I think they're back on now. I hope so. Hopefully I don't have to record this one. Okay, so total load carrying capability of bolts in the area specified is twice this value. So let's call this 2 times the force that the bolt can handle by itself. And so this is 30 kilonewtons total. All right. Now, the force that would cause the bolts to fail is this 30 kilonewtons. And we need to protect that area. But that area has a shear stress acting on it. And the shear stress acting on this area is what we calculated before. We know that we need to protect against a shear stress of 125 kPa. All right. So this is just a force area stress calculation. Okay. So finally, to calculate the spacing required, that's going to come from the area that we need to protect against. We get the force in the bolts, which would cause failure, is equal to the shear stress that we must protect against, multiplied by this area that we're protecting over. Or we're protecting over, again, this shaded area here, right? So it's this area that sort of surrounds these bolts that we're protecting. Okay, so the amount of force that would cause the bolts to fail, 30 kilonewtons. The shear stress that we are going to experience in this area around those bolts is 125 kPa. And the area that the bolts need to protect is the width of the piece multiplied by the spacing that we have. So this is 0.3 times S. All right, so solve for S. And you get here that we need a spacing of 0.8 meters minimum. Bit of an odd problem. It's transforming, there's some shear stress that we have into sort of this longitudinal shear stress that exists between the boards, and then using that to inform the spacing of our bolts required to keep this thing alive. So that's it. Thanks for hanging on through this example problem. I really hope my headphones worked and didn't give out there. I guess I'll find out in a minute. Until we meet again Monday after break. Ta-ta.